You are not audible. You are not audible. You are not audible.
Now,
And now, yes, you are audible.
actually, it is raining outside. That's why I was trying to use the headphone. Let me try again.
But now you are audible.
But
No, when you are not wearing it, as soon as you removed it, you are audible.
no. Let me try again because it is raining outside and I am facing disturbance.
Yeah. Now, okay, you are audible. So you are in a classroom.
Now,
No, sometimes you are becoming inaudible when you wear it.
right now,
Now, yes, the sound is coming.
okay. Okay.
So you are in a classroom now.
No, I am in my room, but it is raining outside. So, and the
Okay.
storm is there. So that's why I am facing some disturbance from outside.
Okay.
Yeah, so I will start with this presentation only, but I will go little bit in my way.
Hello, sir. Good evening. Can you please add me into the Teams group? I think there is some team group where I'm not added yet.
Do you have an email ID? Do you have an account?
Yeah, I have my email ID. I can share in that Q&A.
Can you see the Q&A?
Yeah.
Yeah. Okay. Please give me your. Okay.
Okay, I will.
Even, even
I have
here,
shared in the chat.
here also it may rain.
Sorry, not in the chat, but in the question answer.
Okay. Just give me a minute. Let me check. Try to join it.
Okay. Is it sent on my Outlook?
No. I have sent you the Q&A. Let me reply to your email ID. Yeah. So click here.
Q&A, okay. Yeah, but here I cannot see the group.
Anyway, it doesn't matter because it's almost the classes are going to end and in 2 weeks. And
Yeah, that's
I
fine,
mean,
but I can just go back and see what is there.
okay, you want to see the recording, right?
Yeah,
I think
recording or if other people are there in the group, then I can just connect with them.
no one is in the group. Only you are trying to join.
Okay.
And you are the first one who asked for the joining this
No,
group.
I remember that you said that Yeah, I can see here.
No, what is that group? I don't understand.
No, I mean, when we create any link for you to create the classroom, we first create a group, and in that group we share a link. Like those who have a
Oh,
Microsoft Premium
okay.
account, those who have a
Okay.
Microsoft Premium account, then they can join that group, and the people who are in that group, they can interact with each other as well. More like
Oh,
a WhatsApp or Google, not Meet, but WhatsApp kind of thing. But
oh,
WhatsApp,
okay.
yeah,
Teams. You mean Microsoft Teams?
yes, yes,
Yeah, that
Okay.
link, Teams link.
Team meeting.
yes.
Yeah, yeah. So here I cannot see actually.
Yeah, no one is there, so don't worry.
Okay. You have this
Okay.
site platform, no learning platform. There also you can write questions. You can.
Okay. No, no, that is
Oh,
basically to interact with other people who are
Okay. This is a meeting.
appearing for the
Okay.
exams and all. That's why I
Okay.
needed.
Okay.
yeah, so let's start and let the people join. So it's already 6:09, and maybe after 7:30 I will finish because ah, okay. So we will start with the FaceNet, and the idea of the FaceNet is to recognize any machine that can recognize your face and from either side or any way in a way that it can be used in any kind of security or in any kind of a gateway so that this automated security or gateway can be used in a larger manner. So you don't need a security person to check like if that person is there or not. Okay, and that and in a way that this FaceNet is will be helpful to a person who is trying to have a better security system into their room, in their main gate, or in their company. Just a minute. Yeah. So the idea is that when you give the any input to input any CNN architecture, the architecture should create a embedding. That embedding itself is some kind of output of D dimension. And we are saying that if we are giving the same person to the in a different way, the embedding should be same. Let's say if you are giving your front image of your figure of your face, whatever the trend network that embedding it is creating, it should create a similar embedding or almost same embedding if you are giving a side image of your face. So this is what the target is when this architecture lands. Okay. So idea is when you give an input, forget about the batch file right now. This deep architecture, that is deep CNN architecture. When we call about the deep CNN architecture, the deep means basically the number of CNN layers, like number of deep CNN layers, like n number of sequentially, or maybe with sequences with the you can say the gating, or you can say the residual network attached CNN network that creates an output, and that output is embedding. And before embedding, what we are saying that whatever this architecture is trying to create a d-dimensional output, that output is basically normalized into L2 format. So what does it mean by, like, let's say if it has n number of output, then it will be normalized by its mean of a square root. Like let's say it has a value of 1, 2, 3. Then when it will be normalized, the 1 will become 1 by under root of 1 square plus 2 square plus 3 square. 2 will become 2 by under root of 1 square plus 2 square plus 3 square. And that will be the overall output. Right. So how it is learned, what is the way of training such architecture is that we give a front image, then we give a positive image, and we give a negative image. So the positive image is like the person of the same image, but with the some distortion. Distortions means either it can be a side image, or it can be a image, same image with some shadow, or it can be some rotated image or something like that. So that is the positive image, and the negative image is like a very different person. Like either it can be a front, or it can be a side. And the idea is that the network should produce the embedding such that this whole function F that is creating, it is giving for the of the same person image and the positive image, they should create the output, and the difference between output should be zero. And if the person is negative, that means the different person, the difference should be larger. And in that case, we are giving some margin, and that margin we are saying that after the margin, we will say that the person, if the difference is greater than the margin, then we are saying that the person is negative, and the security does not allow the person to be inside any security gate. Okay. So this is the overall architecture looks like. So basically, this is a simple CNN. There is only one CNN. So it's saying that a simple CNN takes the one input, the another input, and the another input. And we already know that this is the anchor, this is the positive, and this is the negative. And then we will create the output from all three input from a CNN, and then we'll create the triplet loss. So the triplet loss is basically the difference between these two should be always lesser than the difference between these two, or difference between these two, the first one and the last one. So, so how much lesser? And that is what condition we are giving for the alpha. So in this case, we are saying that we are taking the mean square error of the embeddings. Like let's say it has a 5 output, then the respective output should be very similar. And in this case, we will say that the difference of the square, and then we will take the mean, and that should be minimized as a loss function. Okay. So this is what it is. Okay. So this is a very simple testnet, yet quite you can say clever in a way that it tries to understand a same person using an embedding rather than directly trying to understand the same person as a input or as an output. So embedding is basically trying to find the features or trying to create some output such that it always understands a person in a very different ways. So when we learn this kind of method, we always inspire to create something similar in our problem that we are trying to solve. Okay. So you should always think in that way. So this is how the triplet loss is getting created. We are saying that the difference between the anchor and positive plus alpha should always be less than the anchor and the negative. So this alpha is basically the condition we are giving. So this is the minimum margin we want. Even though P comes here or N comes here, then this will considered as a the positive value. So we are giving this margin. Okay. Now comes a simple what we call the convolution network. So we have already understood the convolution network much earlier. If you remember, like I hope you remember because I am only speaking right now. So I'm not showing you any figure right now. So if you don't remember, let me know. So I will try to create figures or something like that. So, or should I create a figure? Create figure. So basically in CNN, what you do, you have any image, then you create a kernel, like a 2D kernel, and then you do the convolution of kernel over the image, right? And then you create the output. And And when you create the output, you call that convolution layer. Okay. When you do such multiple convolution layer followed by any maxful layer or min max layer, you call all of them as a convolution, overall convolution layer, right? So in that sense, you are trying to create, you are undersampling your images. You are trying to downsize your image, right? So you are trying to say that I am trying to create the features of input into the deeper section. When we call when a deeper means, let's say you have a one input and you have passed the 8 kernel. Now you have a 8 output, right? Because each kernel is giving you different outputs. So that is mean the deeper output from a simple image. Okay. So when you do that, however, each image size decreases after each max pool or min max average or anything, whatever you take in that case. And then you try to basically classify this. If you remember the earlier, we were having in the Google Net, we were having 100 different kind of classification. And for each input, we have the 1,000 kind of data. And we were doing the 100 different kind of classification using a Google Net. So in that case, we were basically down sampling our images, and we were also trying to train in between. If you remember, like after a few layer, we were trying to create an overall output, and we were giving condition on that as well. But that condition was regularized using a small lambda like 0.3, if you remember that, right? So, however, like let's say if you are trying to do some segmentation. Segmentation means, let's say you are trying to create an automotive car, and in which you are saying that if your car is moving on the road, uh, then your car must understand the line that is drawn onto the road is what kind of line it is. If it is a dashed line, it is a regular line. If some car is coming from the front side, or it is coming from the rear side, right? Uh, or some tree is in between the road. It can happen in India actually. So yeah, so these kind of segmentation or neural network or automated cars should understand. Otherwise, a chance of you can say a chance of accident is there. So
normalization technique is basically how to compute the mean.
okay, so basically that's why we need the sampling here. Uh, uh, I mean, sorry, segmentation. So when we call about the segmentation, we are saying that whatever the input is, the output should have the same dimension. So basically, this should look something like this. Like if this is my input and it has a pixels of n cross m, then output should have a pixel of n cross m as well. However, when we are doing earlier the classification, we were basically down sampling the size and then we were passing into the MLP to do the classification. However, we cannot do here. So basically, when we are doing the down sampling, we need to upsample as well. And when we need to do the upsampling, in that case, the idea of deconvolution layers come into the picture. So basically, if you can try to imagine it, you are trying to increase the size as you decrease the size, right? So how you can do that? Like when we were adding it using I mean, when we were doing the convolution using the kernels, and then we are doing a max pooling. So max pooling knew that we are trying to find the max of 4 values. But when we want to do the upsampling, we don't have much values to upsample. We have a smaller value, like let's say I have a 4 by 4 value, and I want to convert into 8 by 8. Then we don't know, like if we want to convert the 4 by 4 into 8 by 8, should we create a 8 by 8 weight, something like that, or should I create a 8 by 8 matrix and randomly fill first 4 as the first value, another 4 as the second value, then another 4 as the third value, and another 4 as the fourth value. Like we can do that, but will it help or it will not help? That is the point we need to understand. So either we can do that as well. We can do this as well. But the people who has made this network, they definitely had tried that and they knew that this is not going to help. So they came with a different idea. And the idea was that when they were doing the max pooling, they tried to capture the location. Like let's say if they have the value of 2 by 2 max pooling and then converting into a value. So which quadrant of four values had the max value? And they actually saved a matrix with 1 or 0 where the maximum value was there. They created the matrix with the value 1 in that place and the other value is 0 and that they used for upsampling or you can say the unpooling. Okay. So they are like this is how the segmentation looks like. So basically when this segmentation were done, earlier the people created the data. Like the one you are seeing on the right hand side, people have basically wasted hours or I mean people have given a lot of hours in Microsoft, not Microsoft, basically Photoshop, creating these different layers. And once they have created such layers, then they were using this to teach the network like how they want to do the segmentation and how they want to automate the segmentation. Okay. So basically they created the data, they created the input, they created the output, and they trained over these outputs. Okay. So in this case, you can see the number of outputs they had. The one is the background or the road. The second is the tree. The third is the house. The fourth is the banner. Fifth is this person. And sixth is some kind of barricading. Like you can see the barricading here, the barricading here, something like this. So this kind of classification the neural network has to learn. And this is basically the output data. This is basically the ground truth data that neural network will learn. Okay. So there are different kind of segmentation. So the one that we are seeing here, we are saying that we don't know how much number of car is available in this place. We are saying that wherever this blue one is, that is the car, and we are calling it as a semantic segmentation. However, if we could count the number of car that is coming in front of us, that is called the instant segmentation. So we will understand in this lecture about the semantic segmentation mostly. So
Audible. You're not audible. You're not audible. Are you speaking? You're not audible.
Am I audible now?
Yes. Now again, you're inaudible.
No, then there might be some network problem from your side. You have to check.
No, as soon as you removed it, you are audible.
No, I already disconnected it. So I just removed it because I disconnected.
Okay.
So
We have spoken
So-
something before. We might have missed it.
yeah, so I will repeat it. So basically, I was telling, like when you do the classification, you are creating convolution layer up to this, let's say 256 or 4096. Then after you have a MLP, and then you are doing some classification, right? However, after this training, try to visualize whatever this 4096 convolution layer has learned, and then you will see that it has learned something like this, and it is trying to say that whatever that it has learned here, that is a tabby cat. Okay. However, this input has a dog, it has some background, and also this output has a very lower dimension. So this is not telling me that there is a cat or there is a something here. It just telling me like it has something here. It according to this convolution layer. Okay. So basically we want to say that at the output we want the uh, same size of output, like it has a m cross n, then I want the output as m cross n. So basically we can create a mirror image of this convolution layer, and we will call it as a deconvolution layer. So if you will create the mirror image, basically you are saying that you are upsampling the size, right? And when you are upsampling, how you will do that? That is the question. So so this is how you can do that. Basically, this is what your downsampling looks like. And then you are creating a 32 times sample prediction. So basically, what you are saying. So let's say I have a output of 1/3 of my input. So maybe I will add some zeros such that, and I will add a learning layer, and then I will create my output. So what does it mean learning layer? Like let's say if your input is of 32 cross 32 and your output is of 4 cross 4. So basically you have created a 32 cross 32 matrix. You have filled it with uh, whatever the 4 cross 4 values you had, and then you try to multiply with some kernel vector that is a dimension of 32 cross 32. Okay. So that is called a kind of upsampling, because, and then you will say that whatever the kernel vector I have created of dimension 32 cross 32, that will basically learn to create this segmentation. However, this segmentation is simply creating one step from such small dimension to such large dimension. The learning will be very bad. So basically, you can see in this image here. So it has tried to upsample using one FCN, and this is what they have done. So if this is the ground truth, this picture is not telling me anything about, I mean, you can say in some way that, okay, I am happy with it, but basically it might lead to an accident or any fatality. In that case, we need to create a smaller FCN layers for upsampling. And in that case, we created the residual network such that I want at the end to have this kind of upsampled output or this upsampled output. So either you can directly upsample, that was earlier done. However, you can create a residual such that this is your pool. So you take in between downsampled output, and you created the upsampling using this method, such that first you created a upsampling of 2 times, and then you took the original value, you added them, and then you again did the upsampling. So like your, yeah, like let's say this output is 32 times smaller than the original input, then you want to make it 32 times larger, then you did the 2 times larger, and then you did 16 times larger. However, this is already 16 times larger, so you will do the 16 times larger. So basically, when you are doing the multiple upsampling, so you will create the addition of all those upsampling to create the overall output. And in that case, this kind of output you will get. If you are going for this 8 upsampling, then you will have a better output, right? So like, let's say if this is generating the output will be this. If this is generating the output will be this. And if this is generating the output will look like this. And if you will try to create some relation between all three of them, you will be much closer to your ground truth. Okay. However, we have not seen any up-pooling that I was talking earlier. So it is just simply creating a upsampling using copying the data from here to here and then using some kind of weight. Okay. So these are the paper you can read. Then there was another paper that came into the International Conference of Computer Vision in 2015, when then they tried this kind of deconvolution network that I was talking earlier. So they created this mirror image of this uh, downsampling of the image, and this created this unpooling. So unpooling is basically, this is like when they did the downpooling, they saved this location from where they have copied the data. Like let's say this is the max value. So of this 2 by 2 matrix, I have copied the data, but I have created this switch variable that has a value 1 at this point and the 0 at the other points. And this I will use when I will doing the unpooling. Like I will know that I will copy all the value in this matrix and then I will multiply with the switch variable such that the maximum value will get copied here and the other values will become 0. So that is what the unpooling is. And then there is a deconvolution. Like maybe I will explain that in the sometime later. And you can see that this deconvolution upsampling basically looks something like this. Like you can see, so this is my original image. This is my downsampled image. And then I have done the uppooling. And then I have done the deconvolution. Again uppooling, then again deconvolution, again uppooling and deconvolution and something like this. So you can see that the output J and the input A, they have removed the background and they only, in this case, they are only trying to learn about the bicycle that is available here, right? So how this deconvolution is happening, I will let you know in some time. Okay, let me do that right now. Just a minute. So the scheme is visible, right? Okay. So we are trying to understand the deconvolution. So here we do the convolution, just a very quick introduction. We have this input x0, x1, x2, x3, x4. What we do, we have a kernel, let's say A, B, C. Then we multiply this and we write the y0 that is equal to, we create the padding of A0. So we will write A into A0 plus x0 plus cx1, right? When we write y1, we write this as a, we shift this by one value. So this will become, it will become A, B, C. It will become ax0 plus bx1 plus cx2. Similarly, we can write y2 as a ax1 plus bx2 plus cx3. So basically, we are shifting to the right hand side, right? However, in the deconvolution, we will have our inputs x0, x1, x2, x3, x4. So we will write the y0, y1, y2, y3, let's say. And we will create a transpose such that we will say that I will write the kernel such that this is the transpose of what I had done in the convolution. And then I will write y as y naught as a naught into x naught. I will write y1 as b1 into x naught, y2 as c naught into x naught. However, I will shift this by one stride, and then I will say that, okay, I will add d naught x1, x naught plus a x1, where assume that these are learnable. So these are getting learned, right? So basically, these are not the same thing. Okay. Similarly, I can write y3 as, if I will go one by one stride, then y2 will become cx naught plus bx1 plus ax2, right? So basically, if you are saying that if I am not adding any padding here, then what will happen? My overall, let's say I have a n number of input, and then maybe I will have the output that will that will be lesser than n, right? If I have a stride more than one, then I will have always I will have a lesser than n number of n, right? So similarly, in the deconvolution, if stride is more than one, then let's I have a three input, and if I am having more than one stride, then my second deconvolution will look something like this, right? Let me write y5, y6. So A, B, C, and then A, B, C. Okay. And then we will remove the first value and the last value, because we are saying that when we were doing this convolution, we were adding the padding. So we say that, okay, either we can start from B at, or we can start from A, and then we will ignore the value y0 and y6. Okay. So even though if we are ignoring the first and the last value, we are always getting the value what we wanted. Like this, we have the 3 inputs and we are getting the 5 output. So basically we are upsampling, right? Right. Since let's say if you don't want to do the stride 2, so you can either you can do like let's say this is your x node, x1 or x2. You can create a value between 0 and then create the stride of 1 like A, B, C, A, B, C, A, B, C, A, B, C. So you can see this as you are giving this 0 for the upsampling your data. Like earlier you had 3 data, you upsample to create 5 and then you passed through this stride of 1 into the deconvolution. You got the output like the earlier you have got, right? So basically this is the method of upsampling and then doing the deconvolution like this. Okay. So this is what the upsampling is called and this is what the deconvolution it's called. So basically you can do the deconvolution in 2D images like this. So let's say if you have an image of 3 cross 3, let's say I will keep this value 3. And let's say you have a kernel of 3 by 3. Let's say you have kernel W0, W1, W2. Let's write ABC for now. A, B, C, D, E, G, H, I. Okay, so this is your kernel. So what you will do, basically you will place this, first you will transpose it. So when you will transpose it, it will become something like this. A, B, C, D, E, F, G, H, I, and then pass this middle one to this value. And then first you have to upsample it. So basically, if you are passing the one stride, so try to upsample it something like this. So you can write 1, 2, 3, 0, 0. And then pass this over this. So first you have made the transpose, you have upsampled your original image, and then you got the overall output. So basically your input size has increased and you are doing a you are doing a deconvolution using your this transformed uh, kernel. Okay. So in this case, you have a 3 cross 3. So it won't matter in this case because these are getting learned, right? And these A, B, C, you don't need to transpose it if you have a 2D value, right? Because it doesn't matter, like you are initializing those values and you are doing the same kind of convolution, like you are adding the padding here over this and creating a convolution to create the output of same size. In this case, 5 plus 5. And these are getting learned in the process, so it won't matter, right? So this is basically the deconvolution is. Okay. Let me go to this. Okay. So this is what the deconvolution looks like here, the unpooling and then this layers. So now what you can do that, let's say now you are saying that we want to the semantic segmentation. So we have multiple outputs at the output. So basically we will create like let's say if we have a 5 output, then we will create the 5 such metrics at the output, and we will say that wherever the value of, like let's say I am saying that I am naming the horse as, let's say I have a two value into this image like 1 or 0, like the background in 0 and this horse is 1. Then wherever the output, like when I am creating the ground truth, I will say that my ground truth for horses will be 1, and my for the background the ground truth will be 0, because I have to create the overall loss, right? And in that case I will create this kind of outputs. So let's say in this case, let's say I have a 4 output, and I am saying that like in this case, I have been given here a overall 4 cross 4, but like I can have a 16 different outputs at the output, but let's assume that uh, or you can say that I have a 4 output, but in the first 4 section I have a car. So I will have a 1 values, and each and every other place I will have a 0 values. If the bottom, for the case of car, when I am saying that the prediction is correct, like if the prediction is correct, the network will produce the value 1 here for the car, and it will create the 0 everywhere else. For the horse, this area will become 1 and everything is will become 0. For this, the let's say if this 4 has a man, then this will become 1 and the other will become 0. So that's kind of segmentation that training should produce. Right. However, for the simplicity, we have not filled these values. However, we are saying that, okay, if the car is there, the sum pixel will show the value 1 for that segmentation. For the car segmentation, everything else will be 0. Okay. So basically, this figure is also showing the same thing. So at this place, if the horse is available, the one that is producing the horse, that will show the value 1 at the horse and everything else will be 0. The one that is, like you can see, this prediction is coming, like let's say if my input is producing horse, or we are checking for the horse, then the other thing will show the 0 at this position. Maybe the car will be here, so here will be the 1 and everything here will be 0, here it will be 0, here it will be 0. Right. So this is for the ground truth. However, like when we will be learning, the output will be like, let's say if I am creating a softmax at the output to make the value between 0 and 1 such that they act like a probability. In that case, you can see that they are producing the values between 0 and 1 such that their summation is 1. However, I want this learning such that this should maximize. In this case, I will do the cross entropy loss. So if you remember the cross entropy loss, if you want to increase the distribution and when your values are between 0 and 1, there is a good chance that I mean, when you are doing the binary classification and when you are using cross entropy, then uh, your MSC error will not give you the correct result. There is a good always chance of diverging, right? So we will use the cross entropy loss in a way that this will get maximized and this will get minimized, because they will act as a error. Like when they will be similar, the error will be lesser, and when they will be dissimilar, the error will be higher. This is what the cross entropy loss does, right? If you remember it. So again, we will talk a little bit more about the segmentation. Like let's say this is the output you are getting from your network for different uh, uh, like this is the one output. This is your ground truth, and you are getting the output for car is something like this. Output for horse is something like this. Output for man is something like this, and output for cat is something like this. So in the case of here, I have written the 2. So wherever I have the 2, the man is there, then this value should be maximized in the place of 0, comma 0. Let's say this is 0, comma 0 position, or like if I am calling the position bottom and right side. So this is 0, comma 0. So at 0, comma 0, this should be maximized and other should be minimized. Right. Similarly, if segmentation is saying that at the center part, the 3 is the correct value, then this should be maximized and the other center value should be minimized. So this is what this cross entropy loss will do. Okay. So this is what the overall in this lecture. So I think I have gone quite fast because I am expecting some disturbance. So let's go to the question and let's hope you are able to solve it. Give me a minute. Are you able to see the screen? Yeah, so the question is like if which of the following can be the target output for the semantic segmentation problem with 4 classes? Everyone is there? Yes.
Yes, yes.
Yeah. So which can be the target value for the segmentation of 4 class? So we have seen that if at a position the value is 1, then at the same position the other value should be 0, right? So you can see that here the value is 1 at the same position. So this option is incorrect. Correct? Like let's say if this position is predicting the correct value, then the other classes should not predict the same value at the same position. Right? So this is not the correct option. Option B, you can see that. Let's check with this one. I have a 0 here, 1 here, 0 here, 0 here. This is the correct. I have a 1 here, 0 here, 0 here, and 1 here. So this is not correct, right?
Yes.
The value are matched at this position. If I will go there, so I have a 0 here, 1 here, 0 here, 0 here. Correct? 1,
Yes.
0, 0, 0. Correct. 0, 0, 1, 0. Correct. So nothing is getting repeated here till now. So 0, 0, 1, 0. Correct. 1, 0, 0, 0. Correct. Similarly, 1, 0, 0, 0. Correct. 0, 0, 0, 0, 0, 0, and 1, 1. So basically option C is correct. So not
But
at
option C also, last row is getting repeated na, in a 2 and 3.
Yeah.
In a second class and third class, last row, all are 0, right?
No, here I have a 1 here.
Here you have 1.
Here I have a
Yes.
0.
Yes.
Here I have a 0 and here I have a 0.
Okay.
So at this
Only you are
location,
comparing with the first one only.
no, so I am saying that at each location, only all of them classes, only one should have the max value.
Only one should have.
The max value, like in this case, the 1.
Okay.
Like at this location, I have a 0. Here I have a 1. And this at this location, I am not repeating the 1.
Hmm.
Right? Because
Okay.
1 is telling the correct value. Like at this, whatever the class, I am saying that this second class is correct, predicting the correct value or telling the ground truth for the correct value at this location.
Hmm.
Right?
Okay.
You
If
can
you
see
take
there,
second row.
second row here, like you can see the 0 is here, 0 is here, and then you have the 1 here, and then 0 here. So 1 is at this position, 1 comes 1 here only. So this 1 is not getting repeated at this position.
Okay.
You got it?
Hmm.
Like
Okay. Okay.
I
Right.
hope, right? Like you can see here,
Yeah.
this
Yeah.
1
Got
is
it.
getting repeated, right? So this is not correct.
It is getting repeated. Yeah.
So like this is the one class, this is the one class, this is the second class, this is the third class, and this is the fourth class. The all
Hmm.
class should be unique, right? They should not have a similar value at each location,
Hmm.
right?
Yeah. This is why we call it hard-coded vector.
Yeah, hot vector, hot coded vector. I think this is one hot vector we call it.
Yeah, if you go back, it's written there, hot encoded vector at every
Encoded. Okay, so
pixel.
thought,
So the one would be 1.
yeah.
What is the comment written? It should be 1 if the pixel belongs to that particular class, otherwise 0.
Yes.
Okay.
So I'm talking about this pixel,
Okay.
right? So
Okay.
this pixel has the value 1
Hmm.
here, like
Yes.
this pixel, or else 0.
Hmm.
If that belongs to this class.
You are able to identify it. Okay.
Yeah, but you can see this pixel has value 1 here as well as here. So we don't know which one is the correct, to which class this one belongs or this pixel belong,
Hmm.
right?
Yeah.
So this pixel should be unique to their classes.
Okay.
Okay, so now this is the question. So we have a 1D signal x equal to 1, 2, 3, 4, 5, and we are passing a filter of 1, 2, 3, 4. And we are doing performing a stride of 2 in the transpose convolution on the signal x by the filter f to get the y. What will be the signal y if we don't perform cropping? So basically, I was telling you, like I cropped the first value and the last value. So, so we are not doing that for right now. So what will be the value of y if we are doing the deconvolution in this case? So basically, we will multiply, we will create the transpose of f and then multiply with x. However, we will go with that stride of 2. So basically, I will go to the answer directly. I mean, you can see here. You can see here.
କଲା ଏଥର କହିଲା ଯେ ଟିକେ ସ୍ଲୋ କରିଦେଲା ସେ ଯାଇକି ଆଉ ଦିଟା ଅଛନ୍ତି ଦିଟା
Yeah. So this is my inputs x 1, 2, 3, 4, 5, and this is my kernel. It has been transposed. Then it has been strided by 2. Then again it has been strided by 2, and it has been strided by 2, and here it has been strided by 2. Okay. Now what we have to do? We have to multiply and add. So if we multiply 1 by 1, it will become 1. If we multiply 2 by 1, it will become 2. If we now what we will do? Multiply 3 by 1 plus 1 into 2. So it will become 5. 4 into 1 plus 2 into 2. So it will become 8. Right? So now 3 into 2 plus 3 into 1. So it will become 9. So similarly, we will keep doing this, and this is what the output we will get. However, this is a mistake, so forget about this. This should be 3, this should be 4. Okay. So my correct value should be like 1, 2, 5, 8, 9, 14, 13, 20, 17, 26, and 3 and 4. So my correct value should be A. Okay. So got it how we will do the deconvolution? Any confusion? Okay. Or if you don't want, like according to the question, the stride is 2. However, if you don't want to go for the first stride, you can upsample the original with adding a small 1 zeros in between. And the number of output you will get will be the same without cropping. Okay. So the question is, what are the different challenges one faces while creating a facial recognition system? Different illumination condition, correct? Like let's say half of your face is gone, or when you click your picture, the way you are facing your camera, the illumination will come from that side, and in that case, some feature will be lost. However, the feature that is available, that should be good enough to recognize the person. Okay. So which of the challenges one face? So okay, that is correct. Different pose and orientation of the face images, that is also correct. Limited data of training, correct. Like let's say your company has around 20 people. In that case, you can only train your system for the 20 people. You might create your bad data, like the negative data. But if the negative data is too much, then the bias will be get created for the negative data, and it will not able to find which person is correct. Okay, so there should be a balance. So option D should be the correct, right? So there is the question 4 is, a fully connected convolution network, or FCN, became one of the major successful network architecture. Can you identify what are the advantages of FCN, which makes it successful architecture for semantic segmentation? Anyone? So what does it mean by larger receptive field? It's like, let's say if you are creating a deconvolution network, and then you are having a different layers, like let's say uh, of 1/4 of your original input, or 1/2 of your original input, and they are trying to create the segmentation for your image in a way that, like if your image have multiple features, you can do the segmentation all of them, and you can basically, the point is like larger means you can create the segmentation for all of them in a different way. Okay. Mixing of global features, correct. Lesser computation required, that is also correct. So lesser means lesser is a kind of relative word. So let's lesser to what? Like let's say if you are training a simple classification of any data, and you are only using the MLP, then the uh, number of the weights that you need will be much larger than you had in the convolution layer. That means, let's say if you have an image of 28 cross 28, then in a simple MLP you will have to convert into a 784, right? And that 784 values will be the input for your MLP. And in that case, your weights will be much larger than your what you have into your simple CNN. And even though your weight will be larger, your accuracy will be much lower. So in that case, the FCN is correct for all the three values, all the three options. So now we were talking about the unpooling. So let's say you have a original image. You did the max pool. In the case of the 2x2 max pooling, you will take the value 19, you will take the value 18, 14 and 19. Right? Now the question is, after successive convolution layer, the feature map is again upsampled using max unpooling. Like first you got a convolution layer. Now you are doing the deconvolutioning and you are trying to do the unpooling. So basically you want to know where you are doing the unpooling. So this is your input and you want the output of 4 cross 4. So basically you will save the value where you have got the maximum values. So basically this here should be the 1, here should be the 1, here should be the 1 and here should be the 1, because right? Because when we are doing the max pooling, we are finding the values from these locations. So in that case, this 5 will go to this place, this 6 will go to this place, this 13 will go to this place, and this 8 will go to this place, right? So this 5 and 8 is correct. Even this 6 is correct. And this 13 is correct. So option A is correct actually, right? This is incorrect. And basically we are not, even though this is correct, but we have not multiplied with the value we have got from here, right? That is called switch. Once we will multiply with the switch, the correct option A will be the correct one. Okay. The question is, what could be thought as a disadvantage of fully connected neural network for semantic segmentation addressed by other researchers? Option A is it has a fixed receptive field. So object lesser size than the receptive field will be missed by the network. Correct? Like let's say when you have an image something such that, and when you are creating a pixelated image of that, and such that your image size is such that your whole image come into 1 pixel, that becomes just a color. And in that case, that part of that picture will not be translated for future segmentation, right? So your receptive field is small enough, then that small size uh, classification will not be able to done by the network, right? That is the disadvantage. The option B is the downsampling the image dimension over the depth makes the feature map sparse. So what does it mean by sparse is that, like let's say if you have a matrix and when you are in that matrix, like basically this is a sparse matrix. Okay, like from this matrix you have created upsampled it, and this matrix is basically unsparse because some of them doesn't have any value, or you can call the, so basically you have filled them with 0. Okay. So basically downsampling doesn't make the dimension sparse. It makes, if upsampling makes the space sparse, right? So this is incorrect. It requires a lot of computation. I mean, we have just thought for the case that it requires less computation. So we cannot say that it requires a lot of computation, right? So option A is the correct one. Okay, this question is for the next week. So just ignore it. Even though he has not taught it, but he has kept it here. So ignore this. Hopefully this question will not be in this week. Yeah, so question 9 is in FaceNet, why the L2 normalization layer is used? Okay, so I did not talk about the hypersphere. So let's say if you are having some number and it has a dimension of 2, like let's say if you have a 2D vector. Yes, okay. So if you have a 2D vector and if you are normalizing it with the total values, like let's say you have a value of 1, 2. The first vector is 1, 2. The second vector is 3, 4. The third vector is 5, 6, something like this. And then when you are taking the L2 normalization of each vector, then what will happen? Then these vectors will go to the circle, like it will create a circle, and each vector will go to the radius of that circle in the different directions. If you ever, like let's say, just take a simple 1, 0 and 0, 1, right? And if you will try to normalize it, it will become 1 by under root 2 and 0. And second will become 0 and 1 by under root 2, right? Now, these two value will create a circle with the radius of 1 by root 2. And it will go maximum to this, it will go maximum to the circle. Like when you will create a vector, it will touch the circle with the radius of 1 by root 2, right? So similarly, when you have a three-dimensional vector, then it will create a sphere. And when you will, like when you are doing the L2 normalization, then each vector will touch the sphere in a different theta, beta, and you can say gamma, like because you will have a 3 angle in that case, right? Similarly, if you have a d-dimensional vector, then you will have a d-dimensional hypersphere. Like you cannot imagine the hypersphere, but you can say that uh, the radius of that will be same for each of them, right? With different thetas. Okay. So this is what the L2 normalization does. Okay. The option 10 is, the question 10 is, what is the use of escape connection in, okay, this is also has not been taught and this is in the next week. So, okay, forget about this, but I mean, you can try to solve it. You know enough about the denoising and you enough know about the skip connection. We have studied about the denoising in the autoencoder, right? So if you remember, we said that we had the correct image as the input and then we had the noise in image as the output, and we were saying that we want to create the embedding, or we want to create the latent vector that should be able to classify the image that has some noise as well, right? So first thing is like skip connections are used to create a better input output relation such that there is no chance of you can say what we say losing the gradient, that is called vanishing gradient. And when we talk about the image denoising, we say that we want to test the network such that for the each weight should get trained something for different kind of input rather than creating the identity for a simple input output. Okay. So let's see the option A. Okay. Helping deconvolution layer to recover and improved, that is not correct, because we want them to learn if some this, or there were another idea, like if we are creating noised output, then let's say if my input is a goat that is have a front image, and if my output has a rotated goat, then it should be able to understand it, because they are just trying to understand about the goat. They are not trying to understand about the orientation. So this noising also helps in the orientation, if you remember it correctly. So we are trying to say that when we are trying to do the deconvolution, if my output has some noise, then it should be able to learn the what you can say, a segment that is quite far from what I had trained for, right? So I am trying to remember the benefits of denoising uh, autoencoder, and I can directly relate it with the a simple network that has a denoising at the output, and then it is trying to create a segmentation. Okay. The back propagation of the gradient of bottom layer, which makes the training easy. I mean, skip connection is correct, but not the denoising. Okay, the option A should be correct in that case as well. Yeah, because we are talking about like when we do the denoising, and when we give a rotated image something like this, or little distorted image, they should be able to figure out that they should be able to find the segmentation out of that, right? To create a direct path between convolution layer and the corresponding mirrored deconvolution layer. That is because of the skip connection. Basically, all of them are correct in that case. Well, this is not the correct response, but yeah. So I think in this week, the concepts were quite.
Yes, sir. Actually, I missed one thing. First question, na, that kernel, you have shown some multiplication. No? That could you come, that one, not that one. Yeah, this one. Could you come in this? What is the principle here? Stride is 2. Okay. This one. Yes.
You can see like this is my input, and
Yeah,
I
your
am
voice
doing
has become low.
transpose convolution. Okay. And that is called the deconvolution. Basically, I am upsampling it. So let's say my input is of dimension 5, then my
Yes.
output has a dimension of, in this case, you can connect 2, 2, 4, 6, 8, 10, 12, right? So my output has a dimension of 12. So basically, I am upsampling. In this case, I am creating a filter. I am creating the transpose of that, and then I am multiplying my input with this uh, kernel, and I am getting the output. This is the output. This is
Okay.
my input, and this is the kernel.
Okay.
Okay.
Here you added something, na, next third row, fourth row onwards.
Yeah, this
What
one.
is that? How it
Like,
comes?
so a 3, like this is my kernel value, and this
Ah,
is my input value. So I have multiplied that, and this
okay.
is my kernel value, and this is my input value, and I have
Okay.
added that. Similarly, 4 into 1 plus 2 into 2.
Okay.
So basically, I am upsampling. So this input has become this input.
Uh, okay. So finally, that is the sequence you get 1, 5, 1, 2, 5, 8, 9.
13, 20, 17, 26, and 3 and 4. No,
Hmm.
sorry. No. It's 15 and 20 is the correct value. Sorry. 3 into 5 is 15. 4 into 5 is 20. Okay. I earlier told it was incorrect. Okay. Sorry. So 3 into 5 is
Yeah,
15.
that was correct only. 1
Yeah.
into.
So option C is correct value. Okay. Sorry. Yeah.
Hmm. Yeah, now I got it. Earlier, I was in mute. I was asking, but I was not getting response because I forgot that I was in mute. Sorry
Okay.
for that. Thank you very much for revisiting
Yeah.
the
So this
question.
week was quite simple. Definitely it has a lot of understanding, but mathematically it is very simple. Okay. So
Yeah, because simple things together add for this thing, right?
Yes, yes. I mean,
Sim-
like the people who has tried to create these concepts, they have gone through months and months of thoughts, and they were
Ah,
so.
yeah, when they originally invented these, they must have gone through a lot of thinking.
Yes.
So these are all evolution of evolution, right? Their thinking.
Like, so generally when we do research, we create a thesis in 5 years, but someone comes and tells like, okay, this is so simple, why you took so much time? Then I was like, you are reading it. When you have to create the same thing, you should know,
Yeah. When you
right?
create
So,
something new, you know what is the work involved in it.
yeah, I mean, and the research is the process where you understand like you are just knowing that this works. The one who has done the research, they know what doesn't work, right?
Hmm.
So,
Yeah.
right.
How many ways it will not work?
Yes, exactly.
There will be many ways.
So, like when you will start solving your problem, you might start with this one because you have the basic that, okay, I start with this one and then you can improve over it,
Ah,
right? So, that is what the knowledge means, right? So,
yes,
okay.
yes. Yeah, great. Yes.
Okay, so I will stop this recording and then
Yeah.
we can meet the next week. And then on the Tuesday, I will take the extra classes in which you can ask any doubt. Like
Means
next
you,
Saturday, I will have that. I will have a one class, and then after coming Tuesday, I will have the last class, the
you-
13th
thi-
week.
this Tuesday you will have one class. I mean,
No,
after a few
no,
days. No.
like
Ah,
around
today is
13 or 14, like something like this.
pardon?
13th April or 14th April. I don't remember the exact date.
Yeah. 13th is Monday. 14th is Tuesday.
Yeah, so on the 14th, I will take a last class,
Mhm.
an extra class. So